solving a turbine power, your power always must be positive. If you do a calculation and find that your turbine power is negative, you must know that you made a mistake. You have to go back to your formula and check where you made a mistake. Similarly, with the compressor, if you do your calculations and then you find that your compressor input power is positive, that is a mistake. Your compressor is always negative. So negative does not necessarily mean that there is such thing called negative power. It actually shows the direction of flow. So that's where we are. The first question here is the turbine, where we have a steam with a specific enthalpy of 2990 and the velocity is 16 meters per second. At exit, the steam flow rate, at exit, the specific enthalpy is 2530 and the velocity is 37. Heat loss from the turbine is 25 kilojoules per kilogram, and the mass flow rate is 324,000 kg per hour. Now we assume that there's no mechanical losses, and then we calculate power from the turbine. Now we already have the answer. One thing that we know about the turbine is that our power is going to be positive. If it's negative, then there's a problem. And again, there is a heat loss of 25 kilojoules per kilogram, meaning that your Q is going to be negative because it's a heat loss. It is not heat that is gained by the system, but it is heat lost by the system. So let's quickly draw a schematic diagram and put this information on the sketch. Again, if you look at the specific enthalpy, at inlet is 21 because at that time the steam is very, very hot as it enters the turbine. But when it leaves, the steam inside the turbine is going to expand. As it expands, the temperature drops, and the temperature drops and enthalpy also drops. That's why our H2 is 25 is less than that of that at the inlet. So this kind of information must make sense in your mind that if your answer is wrong, you should be able to see if your answer is right or wrong. So let's draw a quick schematic diagram of a turbine. So turbine is worked out, and then we have inlet, which is 0.1 here, and then we've got outlet at 0.2. So we are told that enthalpy at inlet, H1 is 2990 kilojoules per kilogram. Velocity, C1, 16 meters per second. And outlet, enthalpy at 2 is 2530 kilojoules per kilogram, and the outlet velocity is 37 meters per second. Right. So the and then Q here is negative because it's heat rejected. Now the mass flow rate is 324,000 kg per hour. So what we can do, we can even convert it to kg per second and then divide by 3600. So because we're going to use that kg per second when we calculate our power. Right, so from here now we apply our steady flow energy equation for a turbine. So if turbine, we know that the C1 squared divided by 2 plus enthalpy plus Q is equal to C2 squared divided by 2 plus divided by 2 plus enthalpy of 2 plus turbine work output in kilojoules per kilogram. Okay, so we start now with substitute 16 squared divided by 2000. Why 2000? Because enthalpy is in kilo and Q is in kilo. Our work output is going to be in kilo. Therefore, our kinetic energy must also be in kilo. That's the reason why we divide by 1000 plus 2900, 2990 plus Q. Q is minus 25, is equal to 37 squared divided by 2000 plus 2530 plus turbine work output. So when you work it out, your answer is 34.44 kilojoules per kilogram. But now the question says calculate the power output. Normally, power output is in kilojoules, which is the same as kilojoules per second. So now we have to put a dot here to show that it's a turbine output in kilowatts, which will be mass flow rate multiplied by output per kilogram in kilojoules per kilogram, which is the mass flow rate is 90 multiplied by 434.44, and the output of this particular turbine here is 39.1 megajoules. Sorry, megawatts, or we can say megajoules per second. This is our answer. And you will see from here that the answer is positive, which means that we are dealing with a turbine. And in the exam, if you get a positive answer, you must know that your answer is correct. And what else? What is it that I wanted to explain again about this turbine output? Okay. Yeah, okay. I did explain why we are dividing by 2000. And yeah, I think this is pretty much straightforward. There's nothing really hidden from this. So it's another easy example of a turbine. I'm not sure if I'll ask you something as easy as this in the exam. So again, one thing that I forgot is that next week when we write, no, not next week, on Saturday, when we write our test 2, the question will be specific as to whether the units are in kilowatts or in megawatts, because sometimes if I don't tell students, others will express their answers in kilowatts, which will be 39,100. Others will be in megawatts. So you read the question. The question will say, calculate the turbine output in megawatts or in kilowatts. Otherwise, if you give a different, if you give it in kilowatts instead of megawatts, the system is going to mark you wrong. So please be very careful about the units. Normally, not normally, you don't have to put the units. But when this question says calculate power, some people will use mega, others will use kilo. So the question will say calculate power or turbine power output in megawatts or in kilowatts. And then, yeah, I think, but normally when you put your answer, don't put the units, because sometimes some of the units the system doesn't recognize, and it will mark you down. It will mark you down. I think there's a question on the chat. Let me go back on the chat and check. Sir, can you repeat that? Why divide? Okay, John, the reason why we divide by 2000 is to make our formula, what do they call it, to be dimensional homogeneous. When the formula is dimensional homogeneous, it means that the units for each properties are the same. In other words, remember this C1/2 is the kinetic energy, and then this is enthalpy. This is, so all the units here must be in kilojoules per kilogram. So what work output, kilojoules per kilogram. This H2 enthalpy, kilojoules per kilogram. Now we have to convert meters per second squared to kilojoules per kilogram. In other words, what we have here, our velocity is in meters, not in kilometers. So to make it kilo, we divide by 1,000. That's why we're getting 2,000. Everything here is in kilo, in kilo, in kilo. It is only velocity that is not in kilos. Therefore, to make it a kilo, we divide by 1,000. Right, let's have a look at the second question. The second question, I think, is interesting because it has got a couple of things that are interesting, and the approach of question 2 is different from that one of question 1. So let me increase the font. It is also a turbine. So I'm going to use a different approach, and yeah, so that you understand what is it that we want to achieve here. So let me increase font. Okay, and yes. All right, so let's have a quick look at the question. A gas flows at a steady rate of 4 kg per second. It enters a machine. Okay, a machine. We don't know whether a machine is a turbine or it's a compressor, but we will see. It enters a machine at a pressure of 620 and the velocity of 300 and the specific internal energy of 2100. So these are inlet conditions. And then outlet, the pressure drops to 130. Now, the P1 is greater than P2. It can't be a compressor because a compressor increases pressure. So if the pressure now at P2 is less than at P1, it means that it's a turbine. So we can see from the second statement that now we are dealing with the turbine. The question wanted to be tricky to us to say it's a machine. They didn't want to say a turbine. Maybe to trick us. So this is a turbine. The velocity is 150. The enthalpy is 1500, and the specific volume is 1.2. Whilst flowing through the machine, the heat loss from the gas to the surroundings is 30. In other words, Q is 30. Calculate the density of the gas at entry and exit. The density. So, how do we go about that one? I think I said we're dealing with the turbine. Let me quickly draw a schematic diagram and put this information on the diagram. Right. So P1 is equal to 620. C1 300. Specific internal energy U1 is 2100. And then specific volume V1 is 0.37 cubic meters per kilogram. Now we move on to the second one, to the outlet conditions. Outlet conditions, we have P2 130, and then C2 150 meters per second, and internal energy U2 is equal to 1500 kilojoules per kilogram, and then we have specific volume at 2, which is 1.2 cubic meters. Right, so the first question is calculate what? Calculate calculate the density at inlet and at outlet. So we say A density, we know that the mass balance of any system is given by mass is equal to density, velocity, multiplied by area. That's what we have. So, which is the same as 1, which is the same as, because mass in is equal to mass out. Which you can say that density at 2, velocity at 2 is equal to area at 2. So the question says calculate the density. So the density at 1 is given by 1 divided by specific volume at 1, which is the same as 1 divided by 0.37, which is 2.7 kg per cubic meters. This is our density at the inlet. So the density of gas at the outlet, density at 2, is the same as 1 divided by specific volume of gas at the outlet, which is 1 divided by 1.2, and the specific volume is 0.8 33 kg per cubic meters. So now we have obtained the densities at entry and exit. Now the area at inlet and outlet. Now from here we have mass flow rate, we have the velocities at inlet and outlet, we have the densities, so we can get our area. So B, we said that area 1 from this statement here is equal to the mass flow rate at 1, which is the same as at 2, density at 1 by the velocity at 1, which is the same as 4 divided by 2,7 multiplied by inlet velocity is 300. And the area is 4.938 by 10 to the power minus 3 square meters squared. This is our area. And again, in the exam, I will tell you whether the area must be in centimeters squared, millimeters squared, or meters squared. So it will be clear, especially on online, because online, the system marks only one answer. And then mid-year test, you can give it in millimeters, centimeters is up to you, because correct, if the answer is correct, it's correct. So the system is not programmed to be able to differentiate between millimeters and centimeters squared or meters squared. So area at 2 is going to be 4 divided by density at 2, 0.833 multiplied by exit velocity, which is what, 150. And the answer is 32,01 by 10 to the power minus 3 square meters. So this is the area at inlet and outlet. Now the specific enthalpy at the inlet and the outlet. The specific enthalpy. So specific enthalpy, they want H1 and H2. So H1 is equal to specific internal energy at 1 plus pressure volume at 1, which is the same as V1 is given is 2100 plus P1 is given 620. The specific volume 0.37. And then the answer is 29,4 kilojoules per kilogram. That is H1. H2 similarly is U2 plus P2 V2, which is 1500 plus 130 by 1,2 is equal to 1656 per kilogram. So ladies and gentlemen, I think it must be, you need to understand, when we're dealing with these devices, you don't just do as I do. You must always have reasons why your answer is the way it is. For example, when you look at the specific enthalpies, the specific volumes and all of that. Now, a compressor, what it does, the specific enthalpy at inlet is less than that one of outlet, because when you compress air, heat increases. And as heat increases, now H1, heat increases from H1 to H2. In other words, for a compressor, we're expecting H2 to be greater than H1 for a compressor. Again, by the specific volume again, when you compress air, you make it smaller. When you make it smaller, the volume smaller, it means that at inlet, the specific volume is higher than at outlet, because you've already compressed, you have already reduced the volume of that air. So V2 is smaller than V1 for a compressor. But now in a turbine, it's the other way around. So please sit there and then just look and check all these properties, what happens between a turbine and a compressor. So if you understand what is happening in the compressor, you must understand all the properties. The specific volume is the enthalpy, is the velocity, is what else? Is the pressure. All of these things, they have to make sense to you. Otherwise, if they don't make sense, that is going to be a problem. That is going to be a problem. So what we have in front of us now, it makes sense for a turbine that the enthalpy at the inlet. So I think it's a mistake. It's H1 here. Sorry, it's H1 here, not H2. So because the steam when it enters is very hot, H1 it makes sense to be higher than H2. The specific volume. What about the specific volume? What happens to the specific volume of gas? Because now the expansion takes place. As expansion takes place, the pressure drops as well as the temperature drops. So please make sure that you understand these things, because I don't like people to do as I do. You have to understand what is it that I'm doing and why. And when the answer doesn't make sense, then you should know that no, the answer doesn't make sense. Even this answer here, I think the one that you have on Blackboard, this is the old tutorial. This 686 is wrong. I checked it and then I corrected it. So if you go to Blackboard, you will get a correct power produced. So 686 is close to nothing. I don't think there's a compressor that can give you an output of 686. It's just a very small compressor. The actual compressor, the real compressor, is this compressor here. 39.1 megawatts is a lot of power. So I'm happy with 39.1. But for this particular compressor, for this particular turbine, to give you 686, you should be scratching your head that how can a compressor give me such a small, maybe a compressor, yes, but a turbine cannot give you 686. Otherwise, it's a waste of time to have a compressor giving you close to nothing. This is nothing in terms of power. So let's see. The last question is the power produced by the compressor, by the turbine, sorry, by the turbine. D. The turbine is C1 squared over 2 plus enthalpy at 1 plus Q is equal to C1 squared, C2 squared over 2 plus enthalpy at 2 plus work output. So now when we substitute, we are going to have 300 squared. 300 squared divided by 2000 plus enthalpy, we have already calculated, is 2329. 29.4 plus heat. Heat is negative because it's heat lost by the system, is equal to 150 squared divided by 2000 plus the enthalpy 1656 plus the work output. Okay, so work output here comes to 677,15 kilojoules per kilogram. Now to make it power output in kilowatts, you are going to multiply that value by 4, and the answer will give you 2.71 megawatts. So this is our final answer. You know that this 677 multiplied by 4 is the mass flow rate. It will give you 2.71. So I think from this question you learned two things. Not two things. Yeah, two things. How to calculate the area, how to calculate the density, as well as to calculate the enthalpy if it's not given. You have internal energy as well as the pressure and the specific volume. Again, sometimes we won't give you the pressure and the volumes, but we give you temperatures. When you have temperatures, enthalpy is also given by Cp multiplied by temperature. So if you are dealing with air, we know that air, Cp for air is 1.005. If you're dealing with water, you know Cp for water is 4.187. But normally we deal with water when we're dealing with heat exchangers. But for now, because we're dealing with gas or air, so air is 1.005. Cp for gas will always be given because for gas it's not constant. Can be nitrogen, can be carbon dioxide. So Cp will always be given. If it's not given, it means that we are dealing with air, and air is 1.005. So this H, it will be given, or if it's not given, we give you a temperature, and then you multiply by CP. Or you can use the following formula. So it depends on what you have in your question. So please make sure that you understand this. And yeah, now I think I want us to move to the next question. We have done what do you call a turbine. Let's move on to a question that deals with, let me check if there are any questions on the chat. Second, we have update regarding lab submission. Yeah, Sandile, I normally make announcements after class, not during the class. Can you please do question 4 of this tutorial? I'm not getting 120. Question 4. Okay, Ngozi, let me just do what I prepared. I'll check where you made a mistake. Let me just check, finish what I prepared for the class. The rest will follow. Okay. Right. So yeah, let's we did a turbine. I want us to do a nozzle. A nozzle. Which question is dealing with the nozzle? Question 3, mass flow rate is a turbine again. Question 4 is a what? Is a turbine again. So many turbines. Question 5 is compressor. Okay, I'll do compressor after a nozzle. Where is a nozzle? A nozzle. Where is a nozzle? How come that you don't have a nozzle? A nozzle. Oh, there we go. Question 8. Question 8. Yeah. Question 8. All right. So let's have a look at question 8. Question 8. The nozzle. And I increase the font a little bit so that you can see. Right. So question 8. Nozzles increase the velocity of a fluid. They provide the thrust which propels jet aircrafts and rockets. Other applications include sandblasting and sprinklers. Gas enters is a gas, right? It's not air. So that is very important. You must also differentiate between a gas and air. Gas enters a particular nozzle at a velocity of 60 meters per second. Okay, let me draw a sketch of that nozzle. So these are inlet conditions and outlet conditions. And then the inlet velocity is C1 is 60 meters per second. I'm using a wrong font. Let me change the font color. 60 meters per second. And the enthalpy, H1 is 3025. At entry to the nozzle, the cross-sectional area is 0,1. So the area at that point here is 0,1. A1 is 0,1 square meters. And the specific volume of the gas at the entry is 0,9. V1 is 0,9 cubic meters per kilogram. At exit, the enthalpy is exit H2 is 2790. And then the specific volume is 0,5. Now assumed a perfect thermal insulation. In other words, there is no heat allowed to enter or leave the nozzle, which means it is fully insulated. So this is insulation. So by saying that, it means that Q is equal to 0. Q is equal to 0 in this case. So calculate the velocity of the nozzle at the exit. In other words, we are looking for C2. C2. So for a nozzle, we will apply the steady flow energy equation where we say C1 squared over 2 plus enthalpy at 1 plus Q is equal to C2 squared over 2 plus enthalpy at 2 plus work, input or output. A nozzle, work output or input is 0 because there are no mechanical parts, right? And then because it is perfectly insulated, then Q is also equal to 0. So we are left with kinetic energy at the inlet, kinetic energy at outlet, enthalpy at inlet and outlet. So what are we looking for? We are looking for velocity at the outlet. The velocity at the outlet. Now, how do we do that? We say C2 is equal to the square root of bracket enthalpy at 1 minus enthalpy at 2 bracket multiply by 10 to the power 3 plus C1 squared divided by 2. So the question is, why are we multiplying by 10 to the power 3? This time around, our answer must be in meters per second, not in kilometers. So we are going to convert this enthalpy, which is in kilo, to joules per kilogram. I repeat, when we calculated compressor power, because the units are going to be in kilo, we had to make everything in change the formula, every property there to kilo. Hence, we divided by 2000. But in this case, our answer is going to be in meters per second, not in kilometers. So remember, this H1 and H2 are already in kilo. So to convert them to joules, you multiply by 10 to the power 3. Otherwise, if you leave them as they are, you will find that your velocity, you are expecting your V2, your C2 to be much greater than your C1. C1 is how much? You have C1. I want to check. Yeah, C1 is 60. It's 60 meters per second. So if you don't convert this or don't change this to kilo, you'll find that your C2 is going to be something like 14 or 15 meters per second, which means it's wrong. There's no way in which for a nozzle, outlet velocity can be less than inlet. So a function of the nozzle is to increase the velocity, not to decrease it. So that's why we have to multiply by 10 to the power 3 to convert kilo to joules per kilogram. So we are going to have what? You can just substitute 3025 minus 2790 by 10 to the power 3. I think most of you, the problem is maths, how to get to where I am. It's always a problem. Multiply by 2. Multiply by 2. So the final answer here is 688.19 meters per second. So this nozzle is actually doing its job. It was designed to increase the velocity, and it is increasing the velocity from 60 to 688 per second, meters per second. So I'm happy with my answer. I'm happy with my answer. So I challenge you that, you know what? I know some of you are going to forget this. Go and redo this question here. Don't put this 10 to the power 3 minus 10 to the power 3 here and see how much your C2 is going to be. It's going to be very, very, very low, which means that this nozzle is not doing what it's supposed to do. That's why I said in the beginning that please make sure that you understand the functions of these machines that we're dealing with. If you understand, it's easy for you to recognize that, no, my answer is not correct. It's wrong. But if you don't know what you are doing, you won't even see. For example, if you forget to put that 10 and then you get your C2 as 28 meters per second, if you don't know what you are dealing with, you are happy, you will be relaxed. You say, I know, I'm happy with my answer, because you don't know a function of a turbine. Sorry, a nozzle. But now that you know that if you get something less than 60, there's something wrong with your calculations. Now we have to go back and check. The second question is the mass flow rate. The mass flow rate, we said that the mass flow rate is what? Is density, velocity, and area. Or you can say that the mass flow rate is the same as velocity, area divided by specific volume, because remember density is 1 over specific volume. So inlet velocity is 60, multiplied by area is given as 0.1, divided by specific volume is given as 0.19. So the mass flow rate here is 31.6 kg per second. Right, so please pay attention to these two formulas. If you have area, velocity, and density, you can use that one. If you don't have density but you have specific volume, you use the second one. I'm not sure if these formulas appear on the formula sheet. So if they don't appear, then it means that they must be in your head, in your memory. You have to memorize them. And the last question of nozzles, they want what? They want the area at the outlet. So the area at the outlet, again, we say mass at 2 is equal to velocity at 2 multiplied by area at 2 divided by specific volume. So area, outlet area is going to be 31.6 multiplied by 0.5 then divide by 688.19, and your area is 0.023 square meters. So it means that if you make a mistake with the first one, it is going to affect what? The first one, if your velocity, this velocity is wrong, it means that that value is also going to be wrong, because you are going to use your velocity to calculate your area at the outlet. Okay. Right, so we have done a nozzle, and then I want us to do what is it that we need to do again? Oh, it's a compressor. It's a compressor, and I'm trying to check which compressor question. Let me scroll down. Compressor. I saw a compressor here. Compressor. Okay, no, this is an old tutorial. It does not have question. It does not have question 11. Okay, let me do this. And then good. Let me do this. Okay, tutorial. Okay, that one. Okay, I think I'll have to go to Blackboard, and then I'll have to copy that tutorials. Where are the tutorials? And then it's Open Systems, SFEE. And then copy use question and a centrifugal compressor. Copy. So this is question 11. I'm actually using very old tutorial. It doesn't have question 11. So this is a compressor from question 11 from your TAT. And then I forgot to the answer. The answer there is 176. There we go. Anyway, we know the answer. The answer is 176. 176 kilowatt. What is the answer? Right. So now this is a compressor. Air enters a centrifugal compressor at 1 bar and leaves at the 2.1 bar. So remember, the function of a compressor is to increase the pressure of air or gas. So initially, your pressure P1 was 100 kPa. Now it has increased to 2.1, which is 2,100 kPa. It is doing exactly what it's supposed to do. During the passage of the air through the compressor, the specific internal energy of the air increases by 56, and the specific volume decreases from 0,825 cubic meters to 0,5. It has to decrease because when you compress, now the amount of air becomes smaller, which means that the specific volume decreases, must decrease in the compressor, but increase in the turbine. Assuming the flow is adiabatic. Now, once you say assume that the flow is adiabatic, it means that Q is equal to 0, and that the changes in the kinetic energy and are negligible. Calculate the power required to drive the compressor when the mass flow rate is 135 kg per minute, right? So let's attempt this question here, and we draw a schematic diagram of a compressor, which is similar to that one of a turbine. So for a compressor, inlet is at this point here. And for a compressor, it's work input, not output. So P1 is 100. And then the specific volume at 1 is 0,825 cubic meters per kilogram. And then Q is equal to 0 because it's adiabatic. If it's adiabatic, it means that it is insulated, thermally insulated. So there's no heat exchange between the compressor and the environment. Right, so at 2, the pressure is 210 kPa. And then U2, guys, I think you need to pay attention to this statement here. It says that the specific internal energy of the increases by 56. So in other words, you can say that U2 is equal to U1 plus 56. This is, it increases by 56. In other words, U2 is equal to U1 plus 56. And the specific volume at 2 is 0,5. So these are outlet conditions. Now the question says calculate the compressor power. Compressor power, mass is given as 135. But we don't like 135. We use it. We want 135. Kg per second, not per minute. So the mass flow rate is 225 after dividing by 60. So we apply the steady flow energy equation according to what the question says. So the steady flow energy equation for a compressor is C2 squared over 2 plus enthalpy at 1 plus Q is equal to C2 squared plus enthalpy at 2 plus compressor work input. Because we are dealing with compressor, we are expecting our answer to be negative. Don't forget that. Now, the velocities, you don't have the velocities because the question says that we assume that the kinetic energy is negligible. In other words, the kinetic energy at the inlet as well as the kinetic energy at outlet is also negligible, is 0. We cancel. And then because the compressor is adiabatic, it means that Q is equal to 0. So this guy also falls away. What we have now, we have H1 is equal to H2 plus work input, right? But now H1 is not given, but we have pressures, we have internal energy, and we have specific volumes. So what we can say, instead of H1, we will say that U1 plus P1 V1 is equal to U2 plus P2 V2 plus compressor work input. Okay, so we continue to say that U1 plus P1 is 1 bar, which is 100 kPa, multiplied by a specific volume 0,825 bracket is equal to U2. Instead of U2, you put U1 plus 56. U1 plus 56 plus P2 is 210 by 0,5 bracket work input. Right? So you take U1 to the other side, it becomes negative, so they cancel each other. So U1 is gone. U1 is gone. So what we have now, we have all these values. Now we can say compressor work input is equal to negative 78,5 kilojoules per kilogram. And then from there, oh, sorry, I make a mistake here. It is not, there's no dot here. There's no dot. There's no dot. It's only dot after you have multiplied. So compressor work input is going to be negative 78,5 multiplied by 2.25. And the answer is negative 176,63 kilojoules per second, or you can say just kilowatt. It's up to you. You can leave it as kilojoules per second or kilowatt. It's up to you.